All right, I think it's time to get started. Hello, everyone, and thank you again for joining us today in this webinar on future topics for industrial automation. My name is Nelly Ayon. I'm the Technical Marketing Director of Profibus and PROFINET North America. I'm here with our main presenter today, Michael Baum, Executive Director of PI North America. Let me give you some additional information and details about the webinar before we get started. First, feel free to send us questions in the question tab and any comments through the chat. We will be answering all the questions at the end of the webinar, but it will be very beneficial to have them ahead of time. Also, the slides from today's presentation have a lot of information and many resources. The video recording and PDF of the presentation will be uploaded to the PI North America website in the URL you see on this slide. Well, let's get started by going through the agenda. The title of this webinar is a bit general because there are so many industry drivers nowadays. But today, we'll be covering some specific topics. Starting with an introduction on Industry 4.0, IoT, and PROFINET, following with sections on OPC-UA, TSN, and APL, finishing up with questions and resources. Here is a little bit more about the organization. PI is the Profibus and PROFINET international organization. It is the creator and maintainer of Profibus and PROFINET technologies. It was founded in 1989 with Profibus, and as the industry evolved towards industrial Ethernet solutions, PROFINET was added. A few years later, we identified a necessity for more sensor and actuator technologies. For that, we added IO-Link. Generally, PI has two crucial tasks. One is to educate, another to support. To accomplish that, we have 27 regional associations to support members worldwide. We have competence centers with Profibus and PROFINET experts. We have testing labs for product certification and training centers too. We are part of one of those regional PI associations, PI North America, founded in 1994 as a nonprofit member-supported organization. Within our geographical region, we support also competence centers, testing labs, and training centers locally. And now that you know about the organization, we can get started. Let's start with connectivity. With continuously growing world population, we expect that the count of people will be very impressive, and it certainly is, but compared to the number of connected devices, it doesn't look so extreme. According to this Cisco study, we are expecting 40 billion connected devices by the year 2020. And if you think about all of these devices, you may be picturing your phone, your computer, maybe your tablet. But in reality, the bigger chunk of those connected devices is IoT, or the Internet of Things. The concept that computing power is getting so cheap that we are able to put it everywhere. Another phenomenon is Industry 4.0. In the late 1700s, the first industrial revolution started with mechanization, hydro, and steam power, following the second industrial revolution with mass production and the assembly line. The third industrial revolution in the 60s, 70s brought computers and automation, and the first PLC as we know today. Now we are entering a period of the fourth industrial revolution, which is all about cyber-physical systems. In simpler words, the interrelation between the physical and the virtual world. Industry 4.0 is a worldwide initiative based on very comprehensive theories. Thankfully, there's a simple way to summarize it in a model, the Reference Architectural Model Industry 4.0, or RAMI 4.0. This three-dimensional model describes hierarchically the business, the product lifecycle, and the factory. Industry 4.0 is more than digitalization, virtualization, AI, augmented reality, and all that together. So far, we have IoT, the Internet of Things, with smart watches, smart cars, but also smart robot. Then we have Industry 4.0. That robot and PROFINET sit on the intersection between IoT and Industry 4.0 in the Industrial Internet of Things, or IIoT. Now we have an idea of where does PROFINET stand, and we can get into more details about the protocol. PROFINET is the leading industrial Ethernet standard. It is a globally established and future-oriented technology, suitable for factory, process, and motion control applications. A key factor is a large installed base of PROFINET devices. As you see in the graph, we have almost 21 million devices by the end of 2017 of installed PROFINET nodes. PROFINET has 3 communication channels. The first one is the IP protocol for non-time critical tasks, such as configuration or parameterization. The second one is the real-time challenge for time critical tasks. And finally, the third one, IRT, for the most demanding applications like motion control and drives. In addition, we have worked to support many specific applications through profiles for safety, energy management, drives, and many others. We could talk for days about PROFINET and how does it work, down to the bit and byte, but instead we'll go over the most important piece. PROFINET coexists with our protocols in the same network. If you have a PROFINET network, you are able to use protocols such as OPC UA to send information to the cloud or the office environment. You are also able to use HTTP, SNMP, LLDP, or other protocols for diagnostics and network topology. It is not an open network because you want the information, but because you need it, especially in this world of IoT and Industry 4.0. Data is becoming the new currency. Here is an example. We have 4 turbines that generate 1 petabyte of data, which you can imagine with 15 zeros after following that one. And that's the amount of data they produce every year. On the other hand, if you think about 200 million Twitter users, they generate the same amount of data. Networks are evolving continuously, and the ISA 95 model, which we have on this slide, is changing because the lines between each layer are blurring. All these have caused a lot of data, and now we have many problems that come with this big data, and this is how to access them. And from all these challenges, though, we'll have to overcome over the years, we have identified 6 of them, starting with demand for IT and OT convergence, and almost unlimited access to information, a requisite for deterministic Ethernet, increased TCP and IP communication traffic, integration of field level to higher level systems, and integration of process instruments. The Profibus and Profinet International Organization established a working group for Industry 4.0 to go over a variety of topics. Today, we'll be explaining in detail OPC UA, DSN, and APL as they become key technologies in this industry. Now, I'll be passing the mic to Michael Baum, Executive Director of PI North America, who will take it from here.
Good morning, everybody. Good afternoon, good evening, good night, depending on what part of the world we're in. Again, my name is Michael Baum. I'm excited to present this topic or these topics to you here today on the future of industrial automation. And the reason we're talking about it now is because if in the Internet of Things, it's all about the hot new things that are coming out on the market, your new smartwatch, your new smart toaster, your new smart refrigerator, the industrial Internet of Things, it's all about the data. And so what we're trying to do at PI is make it easy to access that data and create value from it by adding context and turning it into information that you can then act upon. And so within PI, about 3 or 4 years ago, we started a working group. And this was called the Industry 4.0 working group, and it had a number of different topics that it was looking at first. But what we wanted to do was first decide what the actual requirements were for the industrial marketplace before rushing to do any specifications. And so we looked at robustness, we looked at convergence of IT and OT, IPv6, security, gigabit, all of the words that you're seeing on the screen here in front of you. And the reason we have this up against the backdrop of dots and lines connected in a almost in an ad hoc fashion is to suggest that the ISA 95 hierarchy of your ERP system connecting to your MES, to your control system, to your field level really is dissolving, and that these connections are being made in ways that weren't really thought before. You're having field level devices connected directly to higher level systems. And so that brings about thoughts of network robustness as well as security. And so this working group broke off into 3 or 4 different pieces and looked at the 3 most important topics we have today that we're facing, and those are TSN, or time-sensitive networking, OPC UA, and APL, or advanced physical layer. And so what we're going to do is go through these 3 topics in particular and how they relate to us at PI and what we're doing to integrate these technologies to make it easier to get access to data and create value from it. So first is OPC UA. Many of you are very familiar with OPC, particularly OPC Classic, which stood for OLE for process control, object linking and embedding for process control, was based on Microsoft COM and DCOM technologies and essentially made it easy to connect PLCs and HMIs from different vendors. So if you had on your factory floor PLCs from 2 or 3 vendors, A, B, and C, and HMIs from also 3 different vendors, A, B, and C, you'd have to write a particular driver to enable each PLC to speak to each HMI, and you can think of all of the combinations and permutations that are involved with that and the complexities. And so what OLE for process control did was it set up a piece of middleware such that you only had to write the driver once to allow the PLC to speak to the middleware, and then the middleware would distribute the data to the HMIs, again via OPC. Well, in today's world, we have what's known as OPC UA for unified architecture. And what unified architecture means is that it's platform independent. It's no longer dependent upon Microsoft COM and DCOM technologies or any Windows-based technology. You can use it as well on Linux. You can use it on even Android or iOS, or even embedded devices. You're starting to see with OPC UA, where they've got a nano server or nano client, all the way up to cloud infrastructures, AWS, Microsoft Azure, Watson, Predix, whatever, MindSphere, whatever's out there. This scales all the way from the smallest devices up to the largest cloud infrastructure securely. And it does that by installing X509 certificates all the way from end-to-end devices, such that if you move data between these nodes, it does it in a secure fashion. It encrypts the data. And then it does something really particularly important, certainly last but certainly not least, and that's what's known as data context preservation. And the reason that's important is because as we get data from maybe different networks or different sources, no matter the vendor, no matter the protocol, if we look at it, for example, we are showing here on the right-hand side of the screen data that's being translated through something called a companion specification from PROFINET to OPC UA, or maybe Modbus TCP to OPC UA. No matter what, as that data gets moved around a factory or higher level systems, the context is preserved. And that's what's done through something called semantics or metadata. And as that data moves about, you know exactly what you're looking at. It's not just a raw value, it has some extra semantics into it, involved in it, and that really is the basis for turning data into information and therefore providing value. And so the reason we're talking about it here in a presentation from us at Profibus PROFINET North America is because we're looking at how we can integrate factories better, make that data more accessible. And so one of the really the low-hanging fruit for that is machine-to-machine or horizontal integration. This is not a new idea. In fact, if you look back 15 years or so ago, we had a protocol called PROFINET CBA, or component-based automation, which was really nice, but as people realized you could use Ethernet for I/O, therefore we have PROFINET I/O, which is really surpassed PROFINET CBA as the protocol of choice. And so when we were looking at the world of this horizontal integration, we said, well, we could do this in a proprietary fashion, but doesn't it make much more sense to use OPC UA to do that, to allow a PROFINET controller to speak to another PROFINET controller in a cross-vendor interoperable fashion? So whether that controller comes from GE or Siemens or Phoenix or ABB or any other number of companies that have PROFINET controllers, we say, well, let's use OPC UA to do that. Well, that's a nice idea, except up until earlier this year, OPC UA was a client-server technology, meaning that a client had to first say, hey, server, can I connect to you? Server would say, yes, you can. And then the client would connect, and with that three-way handshake, then you started passing data and communicating between them. Well, that doesn't really bode well for a factory floor where you need that real-time exchange of data to let for example, the bottle filling machine, let the bottle labeling machine know that there's a bottle coming off the line and that it needs to get ready to slap a label on it. And so earlier this year, with the latest Part 14 of the OPC UA specification, they came out with a different architecture based on publish subscribe, or pub sub. And so how that works is in a pub sub model, an OPC UA device can simply publish its data, and then whoever wants to subscribe to that data can do that. Now that's really great, except it's still not deterministic. However, what's another technology that's coming around is an idea known as time-sensitive networking, which we'll cover next, which enables that determinism. So you combine OPC UA pub sub with TSN, and all of a sudden you have a real-time machine-to-machine method to move information in a deterministic fashion. The other thing that's missing is safety, and so safety within machine is pretty well defined with ProfiSafe. And what we decided to do within PI is we went to the OPC Foundation organization. We said, hey, we've got this really great method for doing safety based on what's known as the black channel approach, where you essentially ignore the underlying transport and physical layers and just make sure that the data gets from one end to the other. And we said, hey, we're going to open this up to the OPC Foundation and OPC UA such that we can now do machine-to-machine safety, which until now had to be done in a really complex manner and had to be certified by all of the organizations out there, whether it's a UL or TUV, on a case-by-case basis, and it didn't make it very easy. So now that it's an open technology, we hope that this will be adopted very quickly by the market to allow for this machine-to-machine safety. The other neat thing that using OPC UA does, if we look at how we map PROFINET data to OPC UA in a companion specification, it enables not only horizontal integration, but it also enables vertical integration based on TCP/IP. And since PROFINET always has and will be an open network, as we showed on a previous slide about coexistence being an important part of the network, you want to use the right tool for the right task. Well, what that means is that if you want to use the right tool for the right task, you need an open network. You need to be able to use TCP/IP communication in the same network that you run your control over. And so whether you're talking from the controller upwards or even from the device level upwards, having TCP/IP and in some cases with OPC UA on top of it enables that vertical communication. Now we've mentioned companion specifications until now, and so what that means is you take a piece of data, in the PROFINET specification, and you map it to objects or tags in OPC UA. And so we're going to look at how we can do that, and we hope to have a companion spec released. We're looking at 2019 at the moment, and the low-hanging fruit for that, one of the low-hanging use cases that we're going to tackle first is what's known as asset management. So right now you've got factories that have, I mean, there's a factory in Mexico that's got 25,000 PROFINET devices on it. And so when you do that, these weren't all installed at once. And so different devices have different firmware versions, and these are stored in what's known as I&M records on devices. And so we said, what we can do very easily is map these I&M records to OPC UA objects such that it's very easy to grab that information from all of the devices. You don't have to store it in a spreadsheet somewhere that somebody has to refer to. The information might get lost. We want to make it quickly and easily available. And the way that works is like this. So we have an I&M record not only for the processing unit, but also for the control unit. And then everything that processing unit is connected to, for example, let's say this were an IO block or some IO that's being brought directly into the PLC, all of those subunits get a data record that therefore is structured, and all of that data is added. We add metadata to that, and that semantic information therefore then can create what's known as a virtual representation of this object. In the industry 4.0 parlance, that virtual representation is what's known as the administration shell. And so the administration shell is the idea that we can use OPC UA companion specifications or OPC UA information models to basically mimic any machine all the way down to the controller, all the way down to the device level. We can mimic that in a digital fashion so that we create a digital representation of everything on our factory in an idea known as digitalization. And so we've started with asset management records, and we're also looking at diagnostics, because these are two use cases where at the moment, since these are two pieces of information that are sent non-cyclically but in acyclic fashions, we can map them very easily to OPC UA. And the benefits of doing that modeling are that you can now really enable the industrial Internet of Things. And the dream goal of this is you have machines that are able to look at this information model that are self-describing. So self-describing information models mean you don't need a reference manual in order to understand what you're looking at. So one machine can simply look at the information model of another machine. It's going to know exactly what it's looking at. It says, oh, okay, this is a bottle filling machine, or this is a temperature sensor, just based on the information model that it exposes to other machines, and that's really going to enable the industrial Internet of Things. Because if you need an engineer or a human to set up this relationship every time, then it's going to get really, really cumbersome as these connections grow exponentially over the coming years. So by using PROFINET and OPC UA on the same network, by allowing coexistence, we're going to help enable the IT and OT convergence that everybody's talking about. By the way, if you're not familiar with those terms, IT standing for information technology, typically top floor kind of things we're all used to in our day-to-day office work. OT meaning operational technology, or in other words, shop floor, things that are used to manufacture goods. So not only are we going to map PROFINET data into OPC objects, we're going to leverage the OPC UA information models to create virtual representations via the administration shell of all of our devices, controllers, and machines. And really, this enables new business models, and that's kind of the end goal here, is because everything is being done in an open fashion with open specifications and open technologies. Openness is a key pillar of all of this, because we've seen time and time again that openness drives innovation. Because these technologies are open, competition is fostered. Competition forces companies to innovate iteratively and release new service models that simply weren't thought of in the past. So that's why we're doing all of this in conjunction with the OPC Foundation. The second technology that is going to come about rather actually fairly quickly is a concept known as time-sensitive networking, or TSN. And what TSN is, it's the idea that Ethernet is going real time. And when we say here that Ethernet inherits the real-time features which are only available in today's industrial field buses like PROFINET, what we mean is that if we're gonna flatter ourselves, the IEEE organization is essentially not stealing, but they're using a lot of the concepts that we've already brought to market with PROFINET IRT, or isochronous real time. So they're taking those ideas, scheduling, bandwidth reservation, these ideas, time synchronization, and making them into standard Ethernet. And this is being done based on the latest architectural model for bridges or basically switches, which we'll show here in a minute. And the idea is that it's going to be available from commercially available off-the-shelf or COTS chips from companies, from really, particularly commercial companies like a Broadcom or like a Marvell, and not just specific to industrial automation. And the reason that's happening is because there are other industries that are also interested in real-time Ethernet, deterministic Ethernet outside of industrial automation. And so that's why these chip companies are getting involved. For example, in the audiovisual space, this group used to be called the Audiovisual Bridging, or AVB group, until people like the automotive manufacturers were looking at deterministic Ethernet, not only for the manufacturing, which they've done for a long time, but actually for inside the car. The idea was to use deterministic Ethernet because cars these days have so many more sensors, and you've got infotainment systems, and the bandwidth involved in a traditional CAN bus on a car simply couldn't handle all of the data that's being passed. And they don't want 13 different CAN networks just on one vehicle. They want one Ethernet-based network, and they need determinism for that, because when you're driving down the road at 80 miles an hour, you want your ABS system to react extremely quickly to an input from maybe a motion sensor or a radar detector or a LiDAR detector. So the IEEE has really roughly 24 or so standards under this TSN working group. We've listed 6 of them here, having to do with synchronization, 802.1 AS-REV. This is similarly sometimes called IEEE 1588 version 2, a concept we already use in PROFINET IRT. There's something called preemption, where you're going to try and pause a large TCP/IP frame that might be coming out of a device and insert some of your time-sensitive traffic and have that frame wait until that time-sensitive traffic leaves. We're going to do scheduling in the IEEE, path control, and bandwidth reservation. Really, this enables robustness in your networks. There's going to be a redundancy component, as well as we have to figure out how we configure these networks in a concept known as stream reservation, and how we set up these what are called TSN streams. So we've highlighted 6 of these IEEE standards here, but really it's a long list, and you can go to the IEEE website and see for yourself what standards are involved. If you think about where this fits in the traditional 7-layer ISO OSI model, this is really existing at layer 2, at the data link layer. And a little bit, some people are, they can refer to it as layer 2.5, 2 to 2.5. If you're familiar with PROFINET, we have PROFINET RT, real-time, PROFINET IRT, isochronous real-time, and then TSN is just going to be another layer 2, a layer 2 function. So you can have your IP traffic, your TCP IP traffic, your UDP IP traffic, or any other layers 3, 4, 5 through 7 based protocols riding on top of this now deterministic version of Ethernet. And layer 1 doesn't change either. So whether it's 100 megabit per second, whether it's a gigabit, whether it's 10 gigabit, 40 gigabit, it doesn't really matter. And that's the beauty of the ISO OSI models, that these layers are independent from each other. So if you don't modify them and you don't mess with them, you can stack them on top of each other as you choose. So in the past, if Ethernet was based on a best effort principle, and the motivations for that are because the most widely used use case of Ethernet today is the internet, where we want flexibility, and that has come at the cost of determinism. Well, now people are saying in some applications we actually need that determinism, and it's not just in industrial automation anymore. So what this allows us to do is, by integrating the TSN standards into PROFINET, we're going to enable real-time communication, which really has been nothing new for us. We're going to converge IT and OT networks, because now you have a single foundation upon which any protocol can use, not just PROFINET, but now you can have real-time OPC UA, as we talked about before. It's going to use standard chips. It's going to be low latency. And the really important one is that it provides robustness even with high network loads. And the reason that's important is because, as we mentioned before, you got to use the right tool for the right task. And so if that tool is TCP/IP, which is a great tool, well, TCP/IP frames can get really, really big, really, really fast. And therefore, they can bog down a 100 megabit per second network pretty quickly. But what TSN does is it allows you, through bandwidth reservation, to ensure that your time-sensitive data, in this case your PROFINET data, your control data, has a reserved time band on the network, and it gets through without any worry at all. You can take it for granted that your control network will work, and then you just run that best effort TCP/IP traffic as you can. So we have robust networks by default. And the idea is that it's going to be plug and work, or plug and play, depending on the phrase you want to use, and that you should be able to install devices without having to do really complex reconfiguration. And we'll talk about that here in a second. The way TSN works is what we talked about before with TSN streams, which is also called a path. And so what you're going to do is you're going to have a device that says, hey, I want to talk to that PLC over there, and a path is defined for that packet to go. And then in each step of that path through the bridges, and in this case where these are switches, the traffic is prioritized. And if you look deeper into one of these bridges, it's kind of like a roundabout, where you have one ingress, many egresses per port, but on the egress, there is a prioritization lane. So if you have a frame come into one of these bridges, and the way that frame will be prioritized is with something called a VLAN tag. Maybe some of you are familiar with that. This VLAN tag will say, hey, I'm a high priority frame, and I need to overtake any of the best effort packets on the way out. And that's how those high priority, maybe in this case control related frames, will make it through the bridge faster than all of your other best effort frames that have to go through. Well, how is this going to work, and how is this going to be set up? There are really, at the moment, two, I wouldn't say competing, but you could say competing ways to configure the TSN streams. In the first model, this is a centralized configuration model promoted by a group called the Industrial Internet Consortium, or IIC, and they've got a test bed where what they're doing is they're actually scheduling streams one at a time, and their model is to have what's known as a God box, where you put it on the network, and within this God box you're going to say, okay, I'm going to set up every single stream, and this God box is the manager for the entire network. And in this case, they're focusing on lowest latency. The other side is what's known as a distributed configuration model, and this is being promoted by the Labs Network Industry 4.0, or LNI. And their idea is that you don't schedule streams, you simply reserve them. So every device is going to have something called a UNI, or Universal Network Interface, where it simply requests resources from the network. It says, okay, I need these resources from the network. I'm going to be sending this many packets per minute, per second, whatever. They're going to be of this size. You do some sort of bandwidth calculation, and you reserve the bandwidth based on those resources that are requested via the UNI. At the end of the day, it would be a pretty giant failure if we couldn't get these models to coexist in a common TSN network. And so we're making sure that that is going to happen. So whether you use the centralized model or the distributed model, how you configure networks, it has to coexist. And that's currently being done. We're looking at a group in the IEC called IEC 60802, and they're gonna take these IEEE standards and make them an IEC standard. The way it's going to work is how you've always expected it to work. We're going to take the same PROFINET services, the same PROFINET configuration mechanisms, and simply put them on top of TSN. You're going to have flexibility on the physical layer, whether it's copper, fiber, it shouldn't matter. And it's going to be scalable and easy to integrate PROFINET stacks. And that's really nice, because then all of the determinism is handled by TSN. All you have to worry about is, or are, your layers 5 through 7 or layers 3 through 7 protocol integration. So in summary, we're going to ensure robustness even as traffic grows in hyper-converged networks of the future. These networks will be scalable. We want them to be easily engineered. They should be low in cost because the chips are commercially available off the shelf, and it's a future-proven technology because it's simply an IEEE standard. So as the IEEE standard evolves, we will just simply ride that train. The idea is to have the specification released in 2019, which is right around the corner. We're hoping for an April timeframe for that, with first products hitting the market in 2020. And finally, the last topic we would like to cover as part of this webinar is that of the advanced physical layer, or APL. And what this topic is the idea that Ethernet is going to the field level. The reason there's a demand for this is there's a lot of data that is locked up in instruments currently in, for example, in explosive environments, maybe on an oil rig, or maybe in a flour mill where you have particulate matter that can ignite and explode. And as instruments have become more complex over the years, maybe you've got a multivariable transmitter that sends not only temperature but also pressure and volume and things like this. There's a desire to gain access to that data, and that can be a little bit cumbersome with existing technologies, whether it's 4 to 20, whether it's HART, and even in some cases with existing field buses like Foundation Field Bus or Profibus PA. And so there's a demand for bringing Ethernet to the field level. Well, you can't just land an Ethernet cable today on a device in an intrinsically safe zone or div, div 0, div 1, because you're going to create a spark that could cause an explosion. And so what we have to do is limit the current, limit the voltage on the wire such that no spark can be created, and you can land that cable on a device without having to do a purged cabinet or some other mechanical contraption to prevent an explosion. And so this this work was being driven by a group called Namur, and they published a position paper that said, you know what, we don't want this to just be a PROFINET thing or a Ethernet IP thing or a FieldComm group thing. And so we created a cooperation between these three groups. The cooperation will be housed within PI. We're going to be the drivers of this, but we're working equally with ODVA and FieldComm because the two-wire Ethernet APL has to work and enable any protocol to run on top of it. Otherwise, all we're doing is just creating another proprietary field bus, which I don't believe is the future. So like I mentioned before, it's going to be a two-wire connection where we're going to limit the voltage, limit the current. We're going to provide power over the same two-wire cables that provide the communication. At the moment, the idea is to have wired segments that currently exceed the 100-meter limit that Ethernet restricts it to today, because in process plants you often have very, very long cable runs of hundreds and hundreds and hundreds of meters, but it's going to be the same PROFINET protocol running on top of those two wires. This should be available in all zones if you're familiar with those from the European market, as well as available in all DIVs in North America. This is also being done in the IEEE under 802.3 and in the IEC under 679. You can apply up to 60 watts, and it's going to be a switched network, just like Ethernet is today. So you're going to have something like an APL inserter or an APL switch that translates from traditional Ethernet into this two-wire Ethernet, where you're going to have chunk and spurs. If you're familiar with the FISCO model, chunks of up to 1,000 meters into junction boxes of spurs of no greater than 200 meters. At the moment, the idea is to run this Ethernet at 10 megabits per second. And the reason why is that current state-of-the-art technology makes it a little bit difficult to run it at 100 megabits per second, simply because of the, if you think about how you go from 10 to 100 to a gigabit, that's much more power on the wire, and that's exactly what you're trying to limit with intrinsically safe connections. And so at the moment, we're going to start with 10 megabit per second full duplex, and for most instruments, that's actually for virtually all instruments, that should be plenty. The architecture will look like this. You've got a traditional control system with your, whether it's a DCS or a plant asset management, connected to your APL power switch that's in your zone 2 div 2, where it then turns it into APL running up to 1,000 meters out to your field switches. And the field switches are the ones that take the trunks, turn it into spurs, and that's where you do your FISCO calculation, which is a lot easier than the traditional, okay, I've got all these devices, I need to know how much power they are. With FISCO, you can, as long as you limit the things on the devices on the spurs, then you're able to make these calculations very easily, and you can go up to 200 meters with your APL wire from there. Last but not least, the APL infrastructure, as we mentioned before, has two basic components: the power switch and the field switches. And it's going to look like that. If TSN we're hoping to get to the market in 2019, APL is a little bit further off. This is going to be a couple more years until APL is finally specified, and then before first products come out there. But the reason we're presenting it here today in a future topics webinar is because we want you to know that it's something that we're looking at and something that we're actively involved in, and really trying to make it as easy as possible to get as much data from devices and networks, because like we said before, data is the new currency. And so getting access to that data and getting it to higher level systems and creating value from it really is the point of all of this. So in conclusion, before I turn it back over to Nelly, we've identified 6 challenges in the industrial Internet of Things, and through integrating technologies like OPC UA, TSN, and APL, we're going to enable IT/OT convergence. We're going to enable data access all deterministically, maintain coexistence with TCP/IP if you need to use the right tool for the right task, help integrate the field level to higher level systems as the ISA 95 model sort of merges together. And then we're also not only going to do this for factory automation, but also for process control. Okay, I'm going to turn it back over to Nelly, and we're going to go through some resources and have a little Q&A.
Thank you, Michael. Yes, we have some resources here for you. So due to time limitations and we only have an hour here with you, we are able to explain a little bit about all these topics, but there is much more information online, especially on our website. If you haven't been there yet, is us.profinet.com. And I'm already getting a few questions here about the slide deck. So just as a reminder, these slides will be posted in a PDF version and the video on our website under the webinar section, where you can find more webinars and this webinar. We also have some articles for you. We have an MES and PROFINET white paper. We have a very comprehensive APL white paper. We also have some articles from ProfiNews, our newsletter or our blog, about the relationship between the field level and the MES. We also have some campaigns on Industry 4 side, where we talk about Industry 4.0 and IIoT. We share a lot of media, such as videos and articles too. Then we also have a couple of articles, the last two here on Profibus Industry 4.0 and TSN strategy, where we tell you a little bit more of where do we stand as an organization with all of these technologies. Now we have a little bit of time for the Q&A. If you would like to participate, feel free to just send us a question through the questions tab in the GoToWebinar controls. I have a question here for you, Michael, about APL.
Okay.
We have one user asking if they will require additional APL hardware in the device level.
The answer is yes. So if your instrument today only speaks 4 to 20 milliamp and it's just a simple analog instrument, you need extra hardware, for example, to speak Profibus PA. The same will be true for APL. You're going to need special hardware in the device that allows it to speak APL, the 2-wire Ethernet version, because it is a whole new physical layer, and that isn't based on analog 4 to 20 or serial MBP, Manchester encoded bus powered, like Profibus PA was.
All right, thank you. And we have another one here about IRT and TSN. I believe is a user using isochronous real time for PROFINET, and if this is somehow a replacement, it will be replaced by TSN, or if it's just another stream.
Okay, I also saw 2 other questions come in. Can you show again the link where the material will be available? And then the second question was, do we think OPC UA pub sub over TSN will substitute the current OT real-time protocols in the future? What's the PI vision about that? Yeah, we'll address that. So to answer the question about will TSN replace IRT, and the answer is in most cases yes. In the long term, in no way are we going to end of life PROFINET IRT anytime soon. Works really well. Did what it's supposed to do. Does what it's supposed to do. In fact, so well that the IEEE has decided to steal all of our ideas and make them standard Ethernet. But when a lot of those feature functionality becomes standard Ethernet, then you can simply use TSN to handle them. That being said, the current expected cycle times for TSN probably get you down to about 250 microseconds. So if you need a cycle time lower than that, then you would need to use PROFINET IRT. So therefore, we believe that there will still be a market for IRT for sub 250 microsecond cycle times, where we can go all the way down to 31.25 microseconds. And so for those applications, PROFINET IRT will still be relevant. But for the vast majority of them, TSN should be sufficient over the long term. The second question was, can you show the link where the material will be available? Nelly, if you want to just go back one slide, I think that's where you had your resources.
Yeah, and I
Slide.
also, from that question, I have replied to everyone.
Okay.
If you're an attendee, you should be able to see this use.profinet.com and /webinars under our webinar section. It's not currently there uploaded yet because we're still working on it, but you will receive an email with the updated link in a couple of days.
Okay, so now for the $64,000 question, do you think OPC-UA PubSub over TSN will substitute the current OT real-time protocols in the future, and what's the PI vision about it? Well, I don't have 4 or 5 hours to talk about this, even though we could. At the moment, I'm going to answer your second question first, and what's the PI vision about it? The OPC-UA PubSub over TSN idea at the moment, as we said during the slides, is to adopt it for controller-to-controller communication. There are a lot of things that a field bus does besides just moving data. If you look at, for example, if you look at the PROFINET specification, some portion of it is to specify how that I/O is presented in channels and slots and subslots. But much more of that spec is devoted to things like diagnostics and safety and configuration and device naming and all of the other and device replacement and all the other things that a field bus does today that we've gotten to by evolving it over the past 20, 30 years since Profi Bus was introduced in the 80s. And so we've built a lot of knowledge based on that history to know that a field bus doesn't just do moving data from A to B. There are a lot of protocols that do that. And if you were to say, well, OPC-UA PubSub over TSN should be the protocol to do that, I could argue that there are other protocols that move data just as well. And if you put them on TSN, well, now all of a sudden you've got a deterministic way to move data. Who's to say OPC-UA is best? I mean, I like the technology from an industrial automation perspective. It works really well. It's got the security, it's got the information models. But in no time soon will OPC-UA PubSub over TSN replace any of the real-time protocols at the field level. It's not going to happen this year. It's not going to happen next year. It's not going to happen in 2 years. In 5 years, it's anybody's guess. Because the other side of that is something you have to consider about building a factory. Where are the products? It takes thousands of different products to create a marketplace to build a factory. If you go to any modern factory today, you've got products from 20 different vendors in a network of 100 devices. Well, how did it get to that point? It didn't happen overnight. And so to say that, okay, all of a sudden next year or in 2 years, how long is the development cycle for a product? It's at least 18 months. So all of a sudden in 2 years, you're going to have every product with OPC UA pub sub over TSN, and therefore you can replace all of your industrial Ethernet protocols. Yeah, that's not going to happen. So in the short term, what we're looking at is just for controller to controller, because let's be honest, the industrial automation marketplace is slower moving than the consumer marketplace. It ain't like getting a new iPhone every year. I mean, when you install a plant, you want to install it for 15, 20 years such that it runs and you can maximize the ROI on that investment, because you did invest millions and millions of dollars. And so as a result of that, the industry is going to evolve, but there's no doubt that this is a really intriguing technology, and that's why we're embracing it, because it does make a lot of sense for moving information, at least at the controller level. If someday that happens to make it to the field level, well, we're it's yet to be seen. But even if it does, we still promote open networks and coexistence of multiple protocols on the same wire. So if device vendors want to introduce OPC UA in addition to PROFINET on their devices, I welcome it. You use PROFINET for your real-time data exchange. It does that really well, your cyclic traffic, and then use OPC UA for acyclic, and it does that really well. So it's going to be a long time before we expect OPC UA pub sub over TSN to replace any of the real-time Ethernet, industrial Ethernet protocols, if at all.
Yeah, that's true. And we have one more question following. I think it's about connectors. So what type of connectors will be used at the APL instruments, hardwire, M12, etc.?
Yeah, that's a good question. The thought at the moment, and some of this is still in flux because the IEEE standard has not yet been finalized. The thought at the moment is to be able to reuse your existing Profibus PA cabling, because if you have to go out and rip out all of your Profibus PA cabling to install new cabling just to run this advanced physical layer, well, that can be really cost prohibitive and might not make much sense. And so the idea is that you use your existing Profibus PA cabling. Therefore, you'll bring that into your device via screw terminals. So whether it's a Phoenix style contact block or screw terminals on the device. I don't believe that the specification for APL will include anything with connectors. I think that's outside of the scope of the IEEE 802.3CG working group, but I might be speaking out of turn on that one. But at a minimum, we know that how it should work is that it should work over the same Profibus PA cabling, which right now 9 times out of 10 is installed with screw terminals.
Yeah, preserving your investment will probably be the main goal. But if you want to stay updated with anything about APL, all those links on those resources. Also, we post news and updates of what we know from the development of that standard. Do we have any other questions from your end, Michael?
I didn't see any others.
Yeah, me neither.
Well, we're right at about the 1 hour mark. If anybody thinks of any other questions, please feel free to contact Nelly or myself directly, either at via the us.profinet.com webpage where we have a contact us form, or if you have our email, I recognize some of the names on the webinar here today. You can just feel free to email us directly.
Yeah, we would like to hear from you, and we'll be having webinars every few months, updating you in topics. Like I mentioned before, you will get a follow-up email with the link to the presentation, and feel free to reply there and tell us more questions, or if you have any preference for a new webinar idea, we'll be more than happy to take your request. Well, thank you again for joining us. We'll be leaving the webinar running for a minute or so if you would like to submit questions, and then we can reply to you by email. But if not, we will see you next time, and thank you.
Thank you.